Continuing from where we left off, let us look at theorem 6.7. Okay, there are three parts. A, if u of p f alpha minus L of p f alpha smaller than epsilon. Is that the correct notation? Yeah. Holds for some p and some alpha. Holds for some p and some alpha. Then it holds for every refinement of p with the same epsilon. Then it holds for every refinement of p with same epsilon. With same epsilon. Okay. Second, if it holds for p is equal to if it holds for p is equal to x0 to xn, and I have si comma ti in arbitrary points, arbitrary points in what in xi minus 1 to xi, then summation I is equal to 1 to n of f of si minus f of ti is smaller, times delta I, delta xi is smaller than epsilon. Okay? And part C, if f belongs to R alpha and the hypothesis of B holds true, and the hypothesis of B holds true, then summation I is equal to 1 to n f ti alpha delta alpha I minus integral a to b f dx is smaller than alpha. Okay, part A and B are really easy. Theorem 6.4 implies part A implies alpha. Implies A. What does that say? If there's a refinement, then L of the refinement is bigger than L of P, and U of the refinement is smaller than U of P. Okay, so since they're between, you're going to get the difference is smaller than alpha. If you have the assumptions of B under assumptions of B, both f of si and f of ti belong to lion mi to capital Mi, right? Where mi and capital Mi are as before. Thus, well, and so absolute value of f of si minus f of ti is smaller than or equal to capital Mi minus small mi, and thus I have that if I take the summation, I is equal to 1 to n absolute value f of si minus f of ti delta alpha I is smaller than or equal to, well, if I do the same with mi, I get u f, pf alpha I, pf alpha I. And if I do it with small mi, then I get lpf alpha, right? Which proves B, right? Now, use the inequalities that use lpf alpha smaller than or equal to summation f ti delta alpha I smaller than or equal to u p f alpha, and the fact that lpf alpha is smaller than or equal to integral f d alpha smaller than or equal to u p f alpha to prove C. Right? We have shown that both of these are within epsilon range, so they will lie within both of their differences less than epsilon. Okay? Then now we can start talking about which functions should belong to R alpha. Under what conditions can I show that a function belongs to R alpha? Okay? Term 6.8. This is basically saying what functions are integrable. Okay? In fact, it's stronger than integrable because generally when you say integrable, it means just Riemann integrable. Now we are talking about style just integrable. Okay? If f is continuous on a to b, then f is style just integrable on a to b. Proof. This one's relatively easy. Note, f is continuous on closed interval ab means that it is actually uniformly continuous on this interval. So let epsilon greater than 0 be given, right? Choose delta greater than 0 such that alpha a minus alpha b minus alpha a minus alpha a times delta is smaller than epsilon. Okay. Well, sorry. Let me follow the notation of the book. New. What's this eta? Which one's this again? Maybe it's eta. I forget which one this is. Okay, this symbol. Since f is uniformly continuous on AB by theorem 4.19, which says any continuous function on a compact set is uniformly continuous. There is a delta greater than 0 there exists a delta greater than 0 such that whenever I have such that x minus y smaller than delta implies f of x minus f of y smaller than eta. Okay. With t belonging to AB and with with x comma y belonging to AB. X comma y belonging to AB. I don't sometimes understand why they use certain notation. Okay, I'm going to use just x and y. If P is any partition of AB such that delta xi is smaller than capital delta xi is smaller than delta, if if P is any partition of of AB such that delta xi smaller than delta for every I, for all I, then I have mi minus small mi is smaller than which is within f of x, which is within f of x minus f of y. This is smaller than or equal to here. Right? And therefore, technically, it's strictly smaller than nu. Okay? And therefore, yeah, it's eta. I don't know why I keep calling it nu. I know. So this is eta. I mean, I know I keep calling it nu because it looks like an n, but it's an eta. And therefore, what do I get? U of p comma f comma alpha minus L of p comma f comma alpha is, which is equal to summation I is equal to 1 to n mi minus small mi delta xi, delta alpha I is smaller than or equal to well, delta alpha I is smaller than nu. Okay. Mi minus mi is smaller than nu. So nu times summation I is equal to 1 to n delta alpha I. Okay. And what is delta alpha I? If you sum up delta alpha I, that is exactly equal to, not nu, eta times alpha of b minus alpha of a. Okay. And well, by the way I have chosen my eta, this is strictly smaller than epsilon. Okay. And hence, I have shown that therefore f belongs to R of alpha as required. Okay. So this function is styled just integrable. Okay. Theorem 6.9. Well, great. Continuous functions are integrable. What if my function is not continuous? What can I relax on continuity to say, okay, under these conditions, it is still integrable. So if f is monotonic, monotonic on AB, at least on AB, and if alpha is continuous on AB, then f belongs to or alpha. Okay. Note there was an implicit assumption on alpha every single time that alpha is monotonic. Okay. Whenever I'm defining style disintegrals, alpha is assumed to be monotonic. So alpha is still monotonic. Okay. In fact, we were assuming, I think, monotonic increasing rather than just monotonic. Okay. Yeah. My alpha is going to be always monotonically increasing. So monotonic increasing. Okay. Proof. Again, let epsilon greater than 0 be given. Now, for any n, choose the partition Pn. For any n, choose partition Pn such that delta alpha I, which is equal to alpha of b is equal to alpha of b minus alpha of a, alpha of a over n. Okay. Why can you do this? This is because my alpha is continuous. This is because alpha is continuous. And theorem 4.23, which is the intermediate value theorem. Every intermediate value is taken. I look at this values of these values, integral multiples of these values, and I know there is a point where I can take this, I break it. Take that as my xi. Okay. So we can do that. Okay. Now assume f is monotonically increasing without loss of generality, or analogous proof in other case. So assume f is monotonically increasing. Okay. Then I have that mi is equal to f of xi. Small mi is equal to small f of xi, right? Because it's increasing. Wait, xi minus 1. Sorry, xi minus 1. Small m is equal to f of xi minus 1. Okay, because it's increasing. I is equal to 1 to n. And therefore, u pn f comma alpha is minus lpn f comma alpha, lpn f comma alpha is equal to alpha beta minus alpha b minus alpha a over n. Okay, let me write this down in the next line. Is equal to alpha b minus alpha a over n, which is my delta alpha I, times summation I is equal to 1 to n, capital Mi minus small mi, which is f of xi minus f of xi minus 1. Well, all of these are going to cancel, so I get alpha b minus alpha a over n multiplied by f of b minus f of a. And the way I have okay, n is not fixed, so given any epsilon, alpha b minus alpha a is fixed, f of b minus f of a is fixed. I take my n large enough, I can make it smaller than epsilon, but which can be ensured by taking n large enough. Okay. Term 6.10. Okay. Now, suppose instead of monotonic, can I do something even less strict? How else can I go? How can I make the assumptions weaker so that I can get a more general thing? So suppose f is bounded. Suppose f is bounded. F is bounded on AB. F has only finitely many discontinuities, on AB, and alpha is continuous, at every point at which f is discontinuous. So I'm not saying that alpha has to be continuous everywhere, but at least it has to be continuous at every point where f is discontinuous. At every point at which f is discontinuous. Then I have that f belongs to R of alpha. Proof? As usual, let epsilon be greater than 0 be given. Since my function is bounded, let m is equal to supremum f of x. Put m is equal to supremum f of x. Oops. Okay. And let E be the point of all discontinuities of f. Let E, be the set, not point. Be the set of all discontinuities continuities of F. Okay. Well, E is finite and alpha is continuous at every point of E. So you can always find some small interval since E is finite. Since E is finite. And alpha is continuous at E. At E. Every point of E. Every point of E. We can cover E by finitely many disjoint intervals. Cover E by finitely many disjoint intervals. Uj Vj. Uj comma Vj. Such that such that alpha Vj minus alpha Uj is less than epsilon. Okay. Furthermore, we can place these intervals in such a way. We can place these intervals in such a way such that every point of E intersection AB every point of E intersection AB lies in some interior of Vj comma Uj. Lies in the interior of some Uj comma Vj. Okay. Why is this possible? Why can we do this? Why can we find such a Uj and Vj? Well, alpha is continuous at every point of E, right? Even if alpha is discontinuous on the entire AB, even if it has jumps, it is monotonic, increasing, and continuous. So at every point of E intersection alpha, I can find a small neighborhood. Given an epsilon, I can find a delta such that within that delta, everything that lies within that delta is going to have alpha. I will take epsilon prize is equal to epsilon over 2, find the delta for it, and then you can show that alpha Vj minus alpha Uj has to be smaller than alpha. Suppose, okay, let me just write it out maybe. If discount is at say Z, then take ball of ball of take ball take the ball b epsilon over 2 of z. Okay, its pre-image satisfies this condition. Okay, now you have to be slightly careful. The ball of epsilon radius epsilon over 2 might not lie completely inside your continuous interval, right? You have to first find where f is continuous. Find the interval where f is continuous at that point, at z. Take the minimum of epsilon over 2 and the length of that interval, half length of that interval. Okay? And then you can do it. You have to do some slight amounts of things to properly adjust it, but it's not hard. This is just me giving a rough proof on the side for why this works. Okay. Now, here's what you do. Remove the intervals uj comma vj from AB. I have removed finitely many intervals, okay? Each of which is open, so its complement is closed. It's closed and bounded, so it's compact. So the remaining set K, set K is compact. Okay. Hence, F is uniformly continuous on K. Hence, F is uniformly continuous on K. Formally continuous on K. And there exists a delta greater than 0 such that f of x minus f of y is smaller than epsilon if x comma y belong to K and x minus y smaller than delta. Right? Now, here's how we create the partition P. Create partition P as follows. Is equal to x naught, x1 dot dot dot, xn of AB as follows. Each uj and vj must occur in P. Each uj, vj occurs in P. Okay? No point in between uj and vj occurs in P. No point in the segment of any segment uj comma vj belongs to P. Okay? If xi minus 1 is not one of the uj's, then delta xi is smaller than delta. If xi minus 1 is not one of the uj's, then delta xi is smaller than delta. Okay, why am I doing this? Because if I take a point xi, I want to make sure xi minus 1 to xi is completely in K, and in which case it needs, if I take delta x smaller than delta xi smaller than delta, f of the maximum spread in that is going to be less than epsilon, right? This means, note, mi minus small mi is smaller than or equal to 2m for every I. For every I, right? And capital Mi minus small mi is smaller than or equal to epsilon unless xi minus 1 is one of the UJs. Unless xi minus 1 is one of the UJs. Okay? Because if I'm in the compact set, right? If I'm not looking at the interval uj vj, then I'm looking at some partition which involves the delta xi is in the compact set, in which case mi minus 1 is smaller than or equal to epsilon. If I am on the interval mi minus on the interval uj vj, then the best I can say is just capital Mi minus small mi is smaller than or equal to 2m, right? Because all I can say is it's bounded. Hence, therefore, u of p comma f comma alpha minus L of p comma f comma alpha is smaller than or equal to alpha b minus alpha a times epsilon plus 2m epsilon. Okay? Once again, since epsilon is arbitrary, whatever, if I want to show it smaller than epsilon, I can show it for epsilon prime, which is epsilon over alpha b minus alpha a plus 2m. And this shows that f belongs to R alpha. Okay, this proof was a bit more complicated, so this might take you a while to go through it properly. Okay, try drawing out a line. Okay, try drawing a picture of an interval a to b and having some points saying, oh, this is my z1, this is my z2, maybe say, okay, this is my a, this is my b, these are my points of discontinuity, what is happening? Okay, well, I can choose u1 u2 u1 v1 here, u2 v2 here. How is it working out? Okay, draw a picture, it will be helpful. u1 v1, u2 v2. Okay, and fill out the details with a picture if you're struggling to see why it works out, because this proof is very slightly more complicated. Okay. Then last theorem before I stop. Wait, I actually can do slightly more. Theorem 6.11. Let's see how my voice holds up, and based on that, I will make a decision. Suppose f belongs to alpha r on AB. F belongs to r alpha on AB. M smaller than or equal to f smaller than or equal to capital M, phi is continuous on M, phi continuous on small m to capital M, and h of x is equal to the composition phi of f of x on AB. Then, in fact, then h of x belongs to R alpha on AB. Okay, proof. So unlike the previous three theorems, which were drawing conditions for f, when can I show f belongs to AB? F belongs to style just integrable functions on AB. I am assuming this time that f is actually already integrable, and I am trying to say, oh, if I have a function which is integrable and I compose it with a continuous function, the resulting function is also going to be integrable. Okay, let's prove this. Choose epsilon greater than 0, or let epsilon greater than 0 be given, doesn't matter. Sure. Okay, as before, let epsilon greater than 0 be given, doesn't matter. Again, since alpha is continuous, it is uniformly continuous. Is uniformly continuous. Continuous on AB. Sorry, not AB, capital M. There exists delta greater than 0, such that, well, delta is smaller than epsilon, and phi of s minus phi of t smaller than epsilon if s minus t smaller than delta, with s comma t belonging to small m to capital M. Okay. Now, how do you make sure that delta is smaller than epsilon? Simple enough. If delta is bigger than epsilon, then epsilon works, but we want strictly smaller than epsilon, so you take epsilon over 2. Find the minimum of epsilon over 2 and delta, use that one. Okay? Now, since f belongs to R alpha, I know that given any epsilon, there is a partition such that things work out. There is a partition, there is a partition, P-R-T-I-T-I-O-N, partition P, which is x0 to xn, such that of AB, well, of AB, such that u p comma f comma alpha minus l p comma f comma alpha is smaller than delta squared. Okay. Let capital Mi comma small mi have the same meaning as in before. Okay. And be as before. But, and let capital Mi star comma small mi star be the numbers for h. Be the same for h. Okay. So the only reason I'm writing this is because there could be a small confusion. Am I taking capital Mi and small mi of f or h? These are for h, f, and mi stars are for h. Okay. Now, divide 1 to n into two classes. into two classes. First, I belongs to A if mi minus small mi is smaller than delta. Okay, and I belongs to B if capital Mi minus small mi is larger than delta. Okay. Well, for I belonging to A, mi star minus small mi star on those intervals is going to be smaller than or equal to epsilon. Right? In fact, strictly smaller than epsilon. I don't need smaller than or equal to. Smaller than epsilon. For B, there is trouble. Right? It is not obvious that it is smaller than epsilon. In fact, it might not be. But what we can show is that for I belonging to B, capital Mi star minus Mi star is smaller than 2k, where k is the supremum of 5t, where supremum 5t on the interval small m to capital M. So m smaller than t, smaller than or equal to m. Okay. Therefore, delta times summation alpha I is smaller than, well, I just belongs to B rather than I belonging everywhere. Is smaller than or equal to summation I belongs to B mi minus capital Mi delta alpha I, right? Because mi minus small mi is greater than delta in this case. Well, but however, this is still smaller than delta squared. Right? Because the way I constructed my partition was smaller than delta squared. Right? And therefore, I have that summation I belongs to B, alpha I is smaller than delta. Right? If this is smaller than delta, then hence up f alpha minus lp f alpha. Sorry, not f. H alpha is equal to, well, in this case, I belongs to A mi star minus small mi star delta alpha I plus summation I belongs to B mi star minus small mi star delta alpha I, which is smaller than or equal to epsilon times alpha B minus alpha A plus 2 times k delta. Right? Which is smaller than epsilon times alpha B minus alpha A plus 2k, because I took my delta to be smaller than epsilon. Once again, since epsilon is arbitrary, if you give me an epsilon greater than 0, I can take epsilon prime is equal to epsilon over alpha alpha b minus alpha a plus 2k. Use that instead of epsilon here and get that UPH alpha minus LPH alpha smaller than that epsilon, right? And hence H belongs to R alpha as required. Okay. Now, there are a lot of properties of integrals that I will cover tomorrow. Okay. I will stop here for now. This is slightly shorter than usual, but last week, enjoy the shorter times for the exams, for the lectures. Okay.